Hey guys, what's up? Welcome back. Continuing our discussion today of limits and continuity. Might get those exams done today. I finished up another exam over the weekend. Some you guys are up on the list, next in the queue, so I'm gonna get those done today. That's my plan. I should be able to get them done today, no problem. So that's the plan, and I'll let you guys know how it goes after that. But yeah, today, continuing with our discussion with multivariable limits, and we talked about that last time. And yeah, let's see if we can kind of go back over that a little bit today. So we said the limit, so 14.2 continued. And we were talking about things like limit as xy goes to some point AB, f of xy equals L, means that as you get closer and closer to some point AB in the xy plane, specifically when you get to within some radius delta of that point, then your function values should get within epsilon of some number L. For any xy value that you take in there. So again, that was the very formal definition. We used it once last time to prove that the limit existed. Today we're not going to do that anymore. That was the very formal approach. Today we're going to take a different approach. We're going to use polar coordinates to show that a limit exists. But just to recall kind of what we were talking about last time. Also, we said the limit does not exist. So we said limit f of xy does not exist if there are multiple paths to AB, so the point AB, such that they yield different limits. So that's how we showed that a limit did not exist, was by showing that multiple paths yield different limits. So that's kind of everything we went over last time. We also went over the squeeze theorem, and we did a squeeze theorem example in addition to using the definition. So today we're going to use polar coordinates to find the limit of a function. And then we're going to switch over to three-dimensional domains, some functions of three variables, and look at an example there. Let's look at this example. So we're going to say show the limit as xy goes to 0, 0, sine of x squared plus y squared over x squared plus y squared equals 1. So we're going to show that this limit is 1. And how are we going to do that? We're going to let r squared be equal to x squared plus y squared from polar coordinates. So we're basically going to use polar coordinates here. And if we're getting closer and closer to the origin from any direction, that's basically saying r is going to 0. So as x, y both go to 0, that implies that r itself is going to 0. Theta is going to be theta, but r is going to go to 0. So really what we can do is switch this over and we can say this is the limit as r comma theta goes to 0 comma theta of sine r squared over r squared, which is really just a single variable limit because there's only one variable here. So it's really just a limit as r goes to 0, sine of r squared over r squared. And then we use L'Hopital's rule on that. So if we use L'Hopital's rule, L'Hopital's rule would say that this is equal to the limit as r goes to 0. And derivative of the top would be 2r cosine r squared. Derivative of the bottom would be 2r. And now those will cancel. So 2r cancels. And we're just left with cosine of r squared. As r goes to 0, that's cosine of 0, which is 1. Cosine of 0, which equals 1. Which is exactly what we wanted to show. Any questions? Okay, good stuff. Good stuff. So let's continue now. Let's look at continuity next. So continuous functions. Continuous functions. Functions. And the definition. So continuous functions, a function f of xy is called continuous if limit xy goes to ab, f of xy equals f of ab, assuming f of ab is defined. So of course this is assuming f of ab is defined, and assuming the limit as we go to ab exists. So that's what it means to be continuous. Basically just means that the limit is equal to the function value. So it means the limit is equal to the function value. And then we say f of xy is continuous on some region D. So on some region D, if f is continuous at every point in D. So continuity really just means that the limit of the function is equal to the function value, just like we know from single variable calculus. It's the same thing here. The limit is equal to the function value. So example. this example says find all points well, actually I don't think we can do this until we know about polynomial functions. Let's do polynomial functions first. So let's look at definition. A polynomial function of two variables is a sum of terms of the form constant times x to the m, y to the n, where m and n are non-negative integers. So where m and n are non-negative integers. So that's what we call a polynomial function. And then a rational function is a ratio of polynomial functions. So it's a ratio of polynomial functions. And you can probably get a good idea of what those look like already. I'll just throw some out here. For example, you might see something like x squared plus y squared over 2x plus y. That'd be a rational function. Could have something like x cubed y plus x squared y squared plus 3x, and that would be a polynomial. So this right here would be rational. This right here would be polynomial. So when we have multivariable functions, say polynomial and rational, but we have to kind of redefine them a little bit. Let's see. Can we do from here? Well, theorem is that a polynomial function is continuous everywhere. So a polynomial function f of x, y is continuous on all of R2, so everywhere in the xy plane. And then a rational function is continuous within its domain. So a rational function is continuous within its domain. So from here, we can now evaluate limits very easily. If the function is continuous at the point, we just plug it in. Furthermore, we can find the points where the function is not continuous. So let's look at an example. Let's do first just a couple of evaluations. So evaluate part A, the limit as xy goes to the point 2, 3, and the function x squared plus xy plus y squared. And then part B, limit xy goes to the point 1, 1, and then the function xy over x squared plus y squared. So notice polynomials are continuous everywhere. So for part A, f of xy is continuous. So just plug in and get f of 2, 3. So f of limit xy goes to 2, 3 of this function x squared plus xy plus y squared is just going to be 2 squared plus 2 times 3 plus 3 squared, which is 4 plus 6 plus 9, which is 19. So if the function is continuous, we can just plug in the point. Good to go. Now for part B, note that the point 1, 1 is in the domain of the rational function. So limit xy goes to 1, 1, xy over x squared plus y squared is continuous there, so we can just say that that's going to be 1 times 1 over 1 squared plus 1 squared, which is 1 over 2, and that's our limit. So the function is continuous since it's a rational function, and the point is in the domain. We are continuous at 1, 1, so we can just plug it in. I'm just saying over here, just plug in 1, 1 to the rational function since it is continuous at the point 1, 1. Makes life easy when things are continuous. So, of course. Any questions? Slow down, see if there are any questions. Okay, we'll look at a few more examples here today. This example says Example, determine the largest set on which the function is continuous. And our function f of xy is a piecewise function, and it's the function x squared y cubed over 2x squared plus y squared if x is not equal to 0, 0, or sorry, xy is not equal to 0, 0, and then it's equal to 1 if xy is equal to 0, 0. So it defines the function explicitly at 0, 0 because it's not defined there originally. We define it explicitly to be the value of 1. So let's find where it's continuous. So solution, note if xy is not equal to 0, 0, f of xy is a rational function, so it is the rational function whose domain is all of R2 except the point 0, 0. Right, this function is defined everywhere except at 0, 0 because you can't plug in 0, 0 to the denominator. And that's the only thing that messes up this function as far as domain goes. So this function f of xy is a rational function whose domain is all of R2 except the point 0, 0. Therefore, f of xy is already continuous on R2 except at the point 0, 0. Potentially. So now check to see if the limit as xy goes to 0, 0, f of xy equals f of 0, 0, which would be 1. So basically we know that we are continuous everywhere except at the origin. So let's check the origin to see if we're continuous there now. So we know we're continuous everywhere else. Let's check the origin to see if we're continuous there, because we are defined there based on the piecewise part. So let's check to see if there is actually a limit there and if it's equal to 1. So what I'm going to do is switch over to polar coordinates. So I'm going to use polar coordinates. So limit xy goes to 0, 0 of x squared y cubed over 2x squared plus y squared equals hold up. Let's see, I think I wrote a 2 down where I did not mean to at the beginning of the problem. Let me erase that 2 in the denominator. Yeah, we'll do it without the 2. You could ask yourself, what if the 2 is there? And we could go over that later. I think it would still be okay. We'll do it without the 2, and then we'll come back and throw the 2 back in there, see what happens differently. So I'm going to switch this all over to polar coordinates. So this is going to be the limit as r comma theta goes to 0 comma theta. And that's going to be r squared cosine squared theta times r cubed sine cubed theta all over r squared. So what's going to cancel here is this r squared. And that's going to leave us with the limit as r goes to 0 of r cubed cosine squared theta sine squared theta, which is a continuous function. Whoops, it's not just r goes to 0, it's r comma theta goes to 0 comma theta. Now, regardless of what theta does, r is going to 0. So this is going to 0 cubed basically, regardless of what sine and cosine do after you cube them and square them. So regardless of sine and cosine, this thing's going to go to 0 because of the r cubed going to 0. So this is not equal to 1. So f of xy is not continuous. At the point 0, 0. So the set D would be all of R2 without the point 0, 0. And that's a shorthand notation for that. This backslash, backslash, and then put in little set notation, the ordered pair 0, 0. So it's all of R2 without 0, 0. And that's where we are continuous. So everywhere except the origin, basically. So you might ask yourself, what if that 2 had been there in the denominator? So we'll throw that up just for funsies. So what if it's f of xy equals x squared y cubed over 2x squared plus y squared, and then 1 not equal to 0, 0, and then xy equals 0, 0. So then basically everything else is the same, but now we just have to do the limit as r comma theta goes to 0 comma theta, r squared cosine squared theta, r cubed sine cubed theta, over, and this will be 2r, actually, let's rewrite it this way, r squared cosine squared theta plus r squared, because 2x squared plus y squared is equal to x squared plus y squared. I'm basically going to break them up as r squared right here, and then this is going to be r squared cosine squared. So that's how I break up that denominator. And now we can factor out the r squared. So it would be r squared cosine squared, r cubed sine cubed over r squared times cosine squared theta plus 1. And then we would cancel. R squared cancels. And this is going to be pretty much the same thing, 0 still. This is going to be the limit r theta goes to 0 theta. R cubed cosine squared sine cubed over 1 plus cosine squared theta. And this would be 0 everywhere except, well, actually it'd be good to go. So it would always be 0 because that denominator is never going to be undefined for any theta value because we're squaring cosine. So this limit would still be 0. So even if that 2 were down there, we'd still be okay. Questions? So basically the answer for both is that the function is continuous on its domain. Oh, sorry, it's continuous everywhere except the origin. So it's still continuous on the set R2 without the origin. So that's still the place or the set where the function is continuous, even for this function. Of course, it wasn't a radical change, it was just a 2 down there. Okay, let's see. 3 dimensions, or 3-dimensional domains, I should say. So everything is similar for a function of 3 variables. So 3D domains, everything is similar. And by everything, I mean limits, continuity, all that stuff. You could even switch to a different coordinate system, which we'll talk about when we get to chapter 15. We won't come back to this, but we'll talk about new coordinate systems in chapter 15. So, for example, what we mean is maybe find the limit as x, y, z goes to 0, 0, 0. And the function is x squared plus y squared minus z squared over x squared plus y squared plus z squared. And so we have a function of 3 variables, and we want to find its limit at the point 0, 0, if it exists. So the idea is still the same, though. I'm in 3 dimensions here. Well, let me draw it this way. In 3 dimensions, you can approach any point from many different directions. Here we're approaching the origin. So I want to find the limit of this function as we approach the origin. So solution, basically we're going to have a ball of radius delta around our point. So every direction needs to give the same limit. So what we're going to do first is try to show the limit doesn't exist. So try to show the limit does not exist by finding 2 paths that give different limits. That's pretty much the strategy to start with usually, unless it's continuous. If it's continuous, just plug it in. So if it's continuous, plug it in, but I can't plug this in because it's not in the domain. So then I go to, okay, does it not exist maybe? And then try to show it doesn't exist by finding 2 different paths. So I'm going to try the x-axis. So the x-axis. Well, that's basically when y and z are both 0. So we're going to say the limit as x 0, 0 goes to 0, 0, 0. Basically, x is going to 0. And we plug in y and z both to 0. So x squared plus 0 minus 0 over x squared plus 0 plus 0, which is x squared over x squared, which is 1. So this is the limit as x goes to 0 of x squared over x squared, which is just 1, because those would cancel and give a 1. So that's my first path. I can try the y-axis. And that's when x and z are both 0. That'd be the limit as 0 comma y comma 0 goes to 0, 0, 0. That'd be 0 plus y squared minus 0 over 0 plus y squared plus 0. And that would just be the limit as y goes to 0 of y squared over y squared, which again is just 1. So far, I've got the same thing. That doesn't tell me anything. It just tells me along the x and the y-axis, I both get the same thing. It doesn't really say the limit is something. It doesn't tell us anything, except these two give us the same limit. Let's try the z-axis. So the z-axis is going to be when x and y are both 0. So it's going to be the limit as 0 comma 0 comma z goes to 0, 0, 0. That's 0 plus 0 minus z squared over 0 plus z squared, which is the limit as z goes to 0 of negative z squared over z squared, which is negative 1. Aha! Two different paths give us different limits. So this tells us the limit does not exist. If we're going to have a limit, every path has to give the same limit. So any questions? Any questions? If not, I'll do a couple more examples. I have another 2D example. I have a couple more 2D examples we can do. So just more practice. This example, just a 2D limit. Limit as xy goes to 0, 0. Xy squared over x squared plus y squared. Let's see what happens with this one. Can I plug in the point? No. 0, 0 is not in the domain. So maybe I should try different paths. So try paths. So we'll try x equals 0, get the limit, xy goes to 0, 0, get 0 over 0 plus y squared, which is 0. So then we try the path y equals 0, get the limit, xy goes to 0, 0, 0 over x squared plus 0, which is 0. Try the path y equals x, And that'll be the limit as x comma x goes to 0, 0. It'll be x cubed over x squared plus x squared, which is the limit as x goes to 0, x cubed over 2x squared. Cancel that, and we get limit x goes to 0, x over 2, which is 0. Well, it's kind of getting suspicious now. Everything's giving me 0. Let me try one more. Y equals x squared. That goes to the origin, so try x comma x squared goes to 0, 0. So that'll give me x times x squared squared over x squared plus x squared squared, which is going to be the limit as x goes to 0, x to the 5th over x to the 4 plus x squared. Again, I could cancel x squared, but the numerator degree is 5, denominator degree is 4. This is going to go to 0. So maybe the limit is 0. So maybe limit equals 0. So what I'm going to do at this point is switch over to polar coordinates. So try polar coordinates. I mean, you could try the definition, but I'm going to try polar coordinates first. So I'm going to say limit as r comma theta goes to 0 comma theta. And I'm going to get r cosine theta times r squared sine squared theta over r squared. So that's going to be the limit. See, the r squared can cancel here and here. That's going to be the limit as r theta goes to 0 theta. R cosine theta sine squared theta. So again, this is going to go to 0 regardless of what theta does. Theta is going to make sine and cosine oscillate, but r is going to 0, so no matter what cosine and sine are, they're always going to be between -1 and 1, so 0 times that is going to be 0. So this is going to be 0 overall. So the limit is indeed equal to 0. Questions? Well, there's one that has, it's pretty tricky. It's got a radical in it. I don't want to necessarily do it because I want you to try it on your own. There's one in your homework, so I don't want to do it just yet, but I want you to try it on your own. But whenever you see a radical and a limit, what do you think of? You know, from single variable calculus, almost every time you saw a radical, what did you do? You know, what do you have to do with a radical usually in calculus? So I just want you to think about that when you saw a radical. I'll show you what it is. I won't tell you what to do, but I'll show you what the limit may look like. So it could be an example like this. Limit as xy goes to 0, 0, x squared plus y squared over square root of x squared plus y squared plus 1 minus 1. So there's a radical in there. You might be tempted to switch it to polar coordinates. You get r squared over radical r squared plus 1 minus 1. So that doesn't really help a whole lot. I mean, it does a little bit in that it reduces it to a single variable limit, and then maybe you can see what to do. But what do you do with a radical? So tips for radicals? Question mark. What did we do in Calc 1 when we had radicals? So just think about that when you're working through that homework problem. It's a good one. But yeah. Coolio. Any questions? Again, a function of 3 variables could be continuous. You just plug in the point if it's continuous. Polynomial type functions are the same. Products of continuous functions are continuous, etc. So I'll just give you one quick example. I could say the limit as x, y, and z go to the point pi 0, 1/3. The function is e to the y squared times tangent of xz. And whoops, this function f of x, y, z is the product and composition of continuous functions. Hence, it is continuous on its domain. So then the limit of e to the y squared tangent xz, whoops, at this point pi 0, 1/3 is just going to be e to the 0 squared. So just plug in the point times tangent of pi times 1/3. So it's just 1 times tangent of pi over 3, which is square root of 3. So the answer here would just be square root of 3. So for a multivariable function of 3 variables, again, you just plug in the point if it's continuous. And products of continuous functions are continuous. Compositions of continuous functions are continuous on the appropriate domain. But there's nothing really we have to worry about here because xz is defined everywhere. E to the y squared is defined everywhere. So those two are fine. Tangents domain is all real numbers, so we're good to go. So kind of the same rules that applied back in Calc 1 still apply. You just have to think about it a little more carefully in terms of domains and stuff. So any questions? If not, I think we'll wrap it up here. I think that's good enough discussion of limits. We're going to get into double integrals next. We're going to skip over the rest of chapter 14 for ARC class. We'll come back to this in the next course that you take. We call it Calc 4. We'll come back to chapter 14 and finish up, partial derivatives, directional derivatives, all these maximization, Lagrange multiplier stuff in our next calculus course. But we're going to jump into double integrals next, starting on Wednesday. So any questions? If not, I'll see you guys next time. Have a good afternoon.